We are here to discuss a molecule that sustains billions of lives, yet its production is deeply intertwined with our energy systems and carbon emissions. This molecule is ammonia, the foundation of synthetic nitrogen fertilizer. For over a century, the Haber-Bosch process has been the cornerstone of modern agriculture, enabling unprecedented crop yields. However, the traditional method relies heavily on natural gas, making it a significant contributor to global carbon emissions. Our focus today is on the transformative potential of green hydrogen to decarbonize this essential industry, presenting a critical investment opportunity within the energy transition and a pathway to enhanced food security. Modern agriculture, at its core, functions less as a purely biological system and more as an industrial energy system. Consider the food system. The crop yields necessary to feed approximately 8 billion people are now fundamentally dependent on synthetic nitrogen fertilizer, far beyond what natural soil cycles alone can provide. This reliance extends to the chemical system, where ammonia serves as a critical intermediate, industrially synthesized, and then converted into various forms like urea, nitrates, and phosphates. Crucially, the energy system underpins it all. Fertilizer production consumes a substantial 1 to 2% of global energy, with natural gas acting as both a feedstock and a fuel. This direct link means that energy price volatility translates directly into food price volatility, highlighting a profound systemic vulnerability. Despite nitrogen comprising 78% of our atmosphere, plants cannot directly utilize it. The challenge lies in the incredibly strong triple bond of the nitrogen molecule, Nn, which boasts a bond energy of 945 kilojoules per mole. This bond is one of the strongest in chemistry, making atmospheric nitrogen largely inert for biological processes. Natural cycles, such as those involving manure, compost, or nitrogen-fixing legumes, simply cannot provide the scale of nitrogen required to support the yields necessary for billions of people. Historically, before industrial nitrogen fixation, farmland often became exhausted, leading to widespread starvation and even the collapse of empires. The inability of natural processes to meet demand underscored the urgent need for a technological solution. The Haber-Bosch process, discovered in 1909, revolutionized agriculture by providing that solution. This chemical reaction combines nitrogen from the air with hydrogen to produce ammonia. The process requires specific, energy-intensive conditions. Temperatures between 400 to 500 degrees Celsius to activate the iron catalyst, and pressures exceeding 150 bar to force the molecules together. The catalyst itself, typically iron with promoters like potassium oxide and aluminum oxide, accelerates the reaction by a factor of 10,000. Critically, the hydrogen feedstock for this process has historically come almost entirely from natural gas, primarily through steam methane reforming. This is precisely where energy markets become inextricably linked to our global food system, creating both dependencies and vulnerabilities. The scale and impact of the Haber-Bosch process are truly immense. It is estimated that over 50% of all humans alive today are fed by nitrogen derived from this process. Globally, approximately 200 million metric tons of ammonia are produced annually. This industrial activity consumes a staggering 1 to 2% of all global energy. Consequently, the process is responsible for emitting around 500 million metric tons of carbon dioxide each year, a figure roughly equivalent to the total annual emissions from the entire aviation industry. The historical trajectory is equally striking. In 1900, only 8% of global nitrogen demand was met by synthetic means. By 1990, this figure had risen to 88%, and by 2025, it is projected to reach 100%. This underscores its indispensable role in modern food production. The carbon toll associated with conventional hydrogen production, particularly for ammonia synthesis, is substantial. Approximately 95% of all hydrogen produced today originates from natural gas through steam methane reforming. This process, while efficient for hydrogen generation, inherently releases significant amounts of carbon dioxide. Specifically, for every ton of ammonia produced, between 1.6 and 2 tons of CO2 are emitted. To put this into perspective, the total annual CO2 output from global ammonia production matches the entire aviation industry's annual emissions. This highlights that fertilizer is not merely a chemical product, it is an energy carrier deeply embedded within agriculture, carrying a significant carbon footprint that demands urgent decarbonization efforts. When we discuss hydrogen production, it's crucial to differentiate between various pathways based on their carbon intensity and source. Gray hydrogen, the dominant method today, is produced from natural gas via steam methane reforming, emitting around 10 kilograms of CO2 per kilogram of hydrogen at a cost of $1 or $2 per kilogram. Blue hydrogen builds on this by adding carbon capture and storage, reducing emissions to 1/3 kilograms of CO2 per kilogram of hydrogen, with costs ranging from 1.5 per kilogram, and is a growing segment. Green hydrogen produced through electrolysis powered by renewable energy emits virtually zero CO2, costs $2 to $6 per kilogram, and is scaling rapidly. Finally, pink hydrogen, utilizing electrolysis powered by nuclear energy, also achieves near zero emissions, with costs typically between $4 to $8 per kilogram, and is an emerging option. The economics of green hydrogen are undergoing a significant transformation, making it increasingly competitive. Historically, green hydrogen was prohibitively expensive, costing around $14 per kilogram in 2010, while gray hydrogen remained consistently low at about $1 per kilogram. However, projections indicate a dramatic shift. By 2030, green hydrogen costs are expected to fall to approximately $2 per kilogram, converging with and potentially even undercutting the rising costs of gray hydrogen. This cost reduction is primarily driven by the decreasing price of renewable electricity. For instance, producing 1 kilogram of hydrogen via electrolysis typically requires 50 to 55 kilowatt hours of electricity. At an electricity price of $50 per megawatt hour, this translates to a hydrogen production cost of roughly $2.50 per kilogram, demonstrating the clear path to economic viability. The transition to green hydrogen will fundamentally reshape the geography of fertilizer production. In the current gas-dependent model, ammonia plants are typically located near natural gas fields, using gas as both feedstock and fuel. This ties fertilizer supply chains to fossil fuel geopolitics, making them vulnerable to energy shocks that directly impact food prices. The renewable model, however, shifts this paradigm. Plants will be strategically located where low-cost renewable electricity is abundant, leveraging desert solar and coastal wind resources for a competitive advantage. This means new exporters like Chile, Australia, Morocco, and Namibia will emerge, and fertilizer supply chains will follow this new renewable geography. Crucially, this decouples food security from fossil fuel volatility, enhancing global resilience. The production of green ammonia offers a compelling zero-carbon solution for fertilizer. The process begins with renewable electricity, generated from sources like solar or wind power. This clean electricity then powers electrolyzers, splitting water into hydrogen and oxygen. The resulting green hydrogen is subsequently combined with nitrogen from the air in the established Haber-Bosch process to synthesize ammonia. This green ammonia then serves as a zero-carbon fertilizer, maintaining the efficacy of conventional products without the associated emissions. This substitution has the potential to fundamentally reshape the economics and geography of fertilizer production, with countries like Chile, Australia, Morocco, and Namibia already leading the way. Policy drivers such as the US IRA's $3 per kilogram hydrogen credit, the EU's 10 million ton green hydrogen target by 2030, and the Carbon Border Adjustment Mechanism are accelerating this transition. The engineering reality of green hydrogen production presents significant systems challenges primarily around variability. Renewable electricity generation is inherently intermittent, fluctuating daily and seasonally. Ammonia plants designed for efficiency prefer a steady hydrogen supply, making reactor stability a concern. This necessitates robust hydrogen storage solutions to buffer against supply gaps and ensure continuous operation. Low utilization rates due to variability can spread capital costs thinly, rendering projects uncompetitive. However, AI-driven optimization offers powerful solutions. By monitoring real-time electricity prices and integrating with grid data, electrolyzers can be ramped smartly to maximize production when power is cheap or abundant. Dynamic adjustment of reactor throughput based on hydrogen availability and global optimization across energy markets allows plants to become active, dynamic participants, enhancing economic viability. In the evolving landscape of green hydrogen, the ultimate competitive edge will be determined by robust systems economics, not merely by advanced technology. The critical question is, which systems will survive if subsidies diminish, electricity prices fluctuate and utilization rates fall short of projections. The winners will be those projects that secure the lowest cost electricity, targeting corridors with prices below $30 per megawatt hour. High electrolyzer utilization is paramount, as spreading capital costs over more operating hours is essential for profitability. Simplified system architectures will offer a distinct competitive advantage by reducing complexity and operational risk. Finally, stable, long-term demand contracts are crucial for de-risking capital investment. Ultimately, success will hinge on the projects with the strongest, most resilient systems economics. Agriculture represents hydrogen's first truly massive industrial market. The strategic opportunity here is compelling because fertilizer production already consumes enormous quantities of hydrogen. The demand, the necessary infrastructure, and the established chemical process for ammonia synthesis are all already in place. The only fundamental change required is the source of that hydrogen. Consider these facts. Over 100 million metric tons of ammonia are produced globally each year, all of it utilizing hydrogen today. Furthermore, a sophisticated global shipping infrastructure for ammonia is already operational. This sector represents the largest potential hydrogen market if even a fraction of current production shifts to green methods, offering an immediate and substantial pathway for decarbonization. The fundamental molecule remains ammonia, NH3. The core chemical reaction is still the Haber-Bosch process. What is profoundly changing is the origin of the hydrogen feedstock. This shift underscores that hydrogen is not merely about energy technology, it is about transforming entire systems. Few systems on Earth are more critical than the one that feeds the planet. Agriculture is, unequivocally, an energy system, where gas markets directly influence food prices. The integration of green hydrogen into the Haber-Bosch process offers the same reaction, but with zero carbon emissions. Consequently, agriculture stands poised to become hydrogen's first and largest industrial market, driving both decarbonization and enhanced food security.